All right, hey everybody. We're going to do 14.7 today, and we're only going to focus on 14.7. I believe in class I said we went to 14.7 and 14.8, which were polyprotic acids and acid-base properties of salts, but that's going to get really long, so we'll just go with 14.7. If you're keeping up with our nomenclature for what section we're on, this would, I think, be 11.5. So polyprotic acids. Okay. All right. So polyprotic, if you use your terminology, you should be able to figure out that these are acids that can furnish more than one proton. Poly meaning many, protic meaning proton, and they always dissociate in what we want to call a stepwise manner. So that's one proton at a time, and this happens incredibly fast, as you can imagine, but there's never like a complete separation of the protons all at once. One proton comes off, there's a little bit of a time delay, and then the second proton comes off. The conjugate base of this first dissociation, so the conjugate base that is formed after the first hydrogen comes off, becomes the acid in the second step. And I'll do an example problem on the next page that'll show that a bit more. Actually, why don't I just do that now, so you don't have to let that stew for too long. Let me see. Oh, let's pick the most famous polyprotic, probably the one that Pete the Frog is swimming in right now. Poor little guy. This guy. So H2SO4. If we've got that in some water, and we make H3O plus, and then the other thing that we make there is the bisulfate ion, HSO4 negative. This guy right here is the conjugate base. So that is actually what becomes the acid in the second step. Kind of weird, right? The conjugate base becomes the acid. But that's kind of what occurs. So that's our first step. I'm going to erase that now. And then our second step would be for the bisulfate ion, HSO4, to lose its proton. Okay, so it does that. It becomes the sulfate ion, 2 negative, plus H3O plus. Okay. And then this is the new conjugate base right here. Now, I might ask you this question. Which one of those steps, the first step or the second step, produces a, what should I say, has a higher percent dissociation? Which of the steps, the first or the second, has a higher percent dissociation? Well, for a typical weak polyprotic acid, and I guess I could say this for any polyprotic acids, because sulfuric acid is polyprotic, it certainly isn't weak. We can say this, that the dissociation of the first proton, so Ka1, as we might call it, is greater than Ka2. And if we have a triprotic acid, like we'll see in our first example, Ka2 is actually greater than Ka3. So what does that mean? Well, that means that it's much easier to pluck off the first hydrogen ion than it is the second hydrogen ion. So if I draw the sulfate molecule here, it would probably look something like this. There we go. An oxygen. Oops. Let me go back here for a second. Hydrogen there. Hydrogen there. Okay. And if I wanted to pluck off hydrogens, because that's essentially what acids do, they give away their protons, this is going to be easy. Here's the first one. Ready? Watch. That's simple. Simple. Okay. The second one, not so simple. All right. So that one would be more like this. This slow, laborious process in order to get all of the hydrogen to go away. So that second dissociation, a little bit more difficult than that first dissociation. Look at that. I still can't erase it all. There we go. Okay. All right. What else do we want to say? Oh, for a typical polyprotic acid in water, only the first dissociation really matters. The second is not really that important as far as pH is concerned. It does matter if we're kind of keeping track of species that are in solution, but as far as pH, usually the first dissociation is the only one that matters. I certainly will show you problems in which the second one does matter, But 90% of the time, only the first matters. And so that's actually where we'll start with our first example. We're gonna take a look at H3PO4, which is known as phosphoric acid, and you find this inside of soft drinks, dark soft drinks or colas contain phosphoric acid. And let's go ahead and let's calculate the pH of this particular solution. If we think about the first dissociation, the equation would look like this. Plus H2O. We're going to give this an equilibrium sign because this is certainly not a strong acid. Phosphoric is a weak acid. Okay, we get an equation that looks like that. All right, now let's kind of figure out what's happening here. Ka for this first dissociation step is 7.5 times 10 to the negative third, and that equals the concentration of H2PO4 times the concentration of H3O plus divided by the concentration of H3PO4. So if we set up our ice table, remember I said in class today, your ice tables maybe start becoming a little bit overboard right now. You kind of know what's happening. In this case, you've got, if you look at the stoichiometry on the right side of the equation, you've got a 1 here and a 1 here. So that just means our change is going to be x and x. So the top of our equilibrium expression then is just going to be x squared. So let me just erase these guys. I know you guys can't erase. You just have to rewrite it. Sorry. So this is x squared. And then the stuff in the denominator actually then obviously goes out to be 1.0 minus x. Okay, so I'm forgoing the ice table just for brevity's sake. I don't require you to do that by any stretch of the imagination. I think ice tables are great. So 1 minus x on the bottom. Now, as I look at this problem, I'm kind of looking at our exponents here, and I see that these are actually pretty tight. 1.00 and times 10 to the negative third, they're pretty close to each other. I guess I'm a bit reluctant to do this by estimation because of their proximity. So I think I would just crank it out using the quadratic equation. So if you want to do that by yourself, go ahead and pause the video. Otherwise, I'm going to give you the answer real quickly. And here we go. Okay. If you do that, you are going to find out that your pH is 1.08. If you neglected x on the bottom, I think you get something like 1.06. Okay, now, Mr. Cornick, how is this any different from the monoprotic acids that we've been working with? Well, remember, that is not the only dissociation that occurs. We take that conjugate base, it becomes the new acid, we have a second dissociation. Run out of room here. Plus, that's a 2 negative. 2 negative up there. Okay, so we have a second dissociation. And what we'd like to do is figure out, okay, well, how much does that second dissociation add to the hydrogen ion concentration? Because if it adds a lot to the hydrogen ion concentration, then of course it's going to affect the pH. So, from the previous problem, when you solved for x, in the previous problem you solved for x, x equaled the H plus concentration, or the H3O plus concentration. Again, kind of same. So you should have that for this guy already. If you do the same process for this, okay, you do the same process for that, you might ask, well, what do I start with for solution? Well, you're going to probably start just with 1.00. However, let's see, let me think. Yeah, you'll start with 1.00 molar solution because it's a 1-to-1 ratio. Then you go ahead and try to solve for the concentration of hydronium there. And what you would do is you would add those two together to get the total hydronium concentration. And if you're a really go-getter, you could do that for the first one too. So you'd add all three of those together. But what you're certainly going to find out is that because of significant figures, this number right here, let me erase this stuff, this number right here and this number right here are really, really small. So totally small and even smaller. And they really don't add to the top number, which is, relatively big. And so the only dissociation here that plays a factor in the total pH is the first dissociation. Now we will see, like I said before, we are going to see instances where this dissociation does play a factor. So we have to be careful. We can't just totally neglect these guys. There will be times where they're important. All right, sulfuric acid. We use sulfuric acid a lot. It is probably the most important polyprotic. It is the only polyprotic that is classified as an angry acid, so it kind of gets its own little section in the book. Wow, really cool. So AP always treats sulfuric in this way. And this is, I think, to speed things up. First of all, the first dissociation, so the first hydrogen ion that comes off, that's a strong dissociation. That thing dissociates 100%, all right? The second hydrogen that gets pulled off of there, out of the bisulfate ion, is weak. And so we need to use the Ka for that particular dissociation in order to calculate the concentration of the hydrogen ion. Now this is the one acid where that second dissociation is actually sometimes really makes a difference, and we really want to calculate that. So this is the number, and this obviously would be given to you on a test, but you're going to use this quite a bit, I think, in your problems here. 1.2 times 10 to the negative second. That's the number for the dissociation of acid. 1.2 times 10 to the negative second. Okay, so when you're doing problems with sulfuric acid, that's what you'll use for Ka. All right, so this is where I want to stop for today. I want to show you this table because it's a nice kind of wrap-up summary now that we've talked about acids, and we've talked about bases, and we've talked about strongs, and we've talked about weaks. Because the one thing that I always enjoy thinking about is, well, what happens when you mix bases and acids? Because there seem to be opposites. Well, this table kind of tells us the characteristics of those types of reactions, and we'll get in depth with it a little bit more on Monday night. But it's kind of neat to see that if we got a strong acid and a strong base, we got this top one up here, strong acid, strong base, like HCl and sodium hydroxide, we're going to mix those two together, and we should find that at the end of the day we get a pH equal to 7. A strong acid and a weak base. Now that's a little bit different. Okay, so what do we think would happen with a strong acid and a weak base? Well, we've got HCl, strong acid, weak base is ammonia. You mix those two things together, and we should be able to come up with the idea that the pH is still going to be less than 7. So we've got what we call equimolar concentrations of HCl and NH3 at the same amount of each. Your pH is going to be less than 7 because HCl is just better at giving away its proton than NH3 is at accepting it. How about if we kind of flip the tides a little bit? Is there going to be a difference here? Well, sure there will. With the weak acid plus a strong base, and the opposite is true. Then the pH here is going to be greater than 7 because the base is going to be a little bit stronger. It's going to be more willing to accept the proton or give away its hydroxide than the acid is willing to actually donate the proton. And then the final one, which is the one, like I said, we'll talk about more on Monday because it's really intriguing. What about a weak acid and a weak base? Now, this is tough stuff. So if you get a weak acid and a weak base, it's not cut and dry. It's not like, well, strong acid and strong base, well, it's neutral, so weak acid, weak base should be neutral too. Not necessarily. So this pH actually is dependent on two things. It is dependent on the Ka, the acid dissociation constant, and the Kb, the base dissociation constant, of the conjugate acid and base. So these guys. Okay? So it totally depends. The first three doesn't depend. If you have those three situations, you know where the pH is going to fall. The last one, though, it totally depends on what it is you're playing with. And that's what makes for some cool chemistry math. So, again, we'll get into that next week. All right. For the rest of the weekend, then, if you did not finish those problems in class today, which I'm sure you did not, please give those as hard of a try as you can. If you got questions, jump on Edmodo. Maybe I'll check that a couple times to see if I can help you out. We need to kind of plow through those as best as possible. And you can expect a quiz on Monday that's going to focus on bases and calculating pH and concentrations of bases. All right, that's the end of the video.